So the next talk is Parser Differentials when interpretations becomes a vulnerability by Joern from GitLab security team.
Hi everyone, welcome to my little presentation here. My name is Joernchen, also known as Joernchen on the internet. I work at GitLab's security research team, and I like Parser differentials. Before I was in the security research team, I was like 10 plus years in security consulting, and at some point I somehow got into that topic, and it always kind of fascinated me. So I would like to present a few things here. But first of all, who knows this meme? This meme template, is this known? Yeah? Inside of you are two JSON parsers. And one says you're an admin, and the other one does it not. And this is basically the gist of the talk. This is the idea. You have two parsers, and they disagree, and we're trying to maximize the profit we can make with it. So first, a little disclaimer. This talk will not have any academic background. I have a very, very tiny academic background. I consider myself a successful dropout out of university. So I never finished. And to everybody who's still studying, please don't do this. Don't be like me. I will not have a complete overview about this topic at all. And I will specifically not talk about fuzzing. Instead, I will give my kind of journey through Parser differentials with some nice practical examples, and I will show, unlike in the keynote, we had a very hard to exploit vulnerability, I will show some very easy to exploit vulnerabilities, yet they are sometimes not that easy to spot. So I just said this is not going to be academic, but the first thing I do is citing an academic paper for the definition of a Parser differential, which is like Parser differentials emerge when two or more parsers interpret the same input in different ways. What is this good for? Like, I mean, that depends, right? It always depends. In many bug classes, you know what it's good for. Like a memory corruption, write primitive, you can write memory with the content of your choice at a address more or less of your choice. Or with the SQL injection, you can modify a SQL statement on the server side. But for Parser differentials, it's very much dependent on the context, how the parsers are used together. Like, is it one HTTP front end versus one HTTP backend? Is it one XML parser here and one XML parser there in two different components which exchange SAML messages, for instance? But what's cool about Parser differentials, I mean, to find a memory corruption bug, you have to have a piece of software which implement that memory corruption. For a Parser differential, you can just take two parsers for the same format and try to compare them and kind of stockpile on Parser differentials without any further meaning. But then, when you need them, you have them. I'll come to that example a bit later in my presentation. But first, I want to showcase a bug of Max Justice, which personally was the one, I think it was from 2018 or so, 2017, 2018, around that time, which got me interested in that topic because it very nicely showcased this concept. So it's CouchDB RCE, and it was caused by a Parser differential. CouchDB is written in Erlang, but you can have JavaScript code which verifies documents you want to store in that database. And if we compare just the example from the two wolves, basically a duplicate key in JSON would give you an array of those key value pairs in the library Jiffy, which was used in CouchDB. And in JavaScript, it would just take the last value it sees under that key. That is interesting, and it is problematic because those validations were also used on those JavaScript validations were used on user objects. And if we look at the Erlang implementation, so this is basically cut and paste from the blog post. If we look at the Erlang implementation, it would just take the first result out of this array for the getter of this object, and for JavaScript it would give you the second variant of whatever stored under this key. And the payload for creating a user which exploited this vulnerability, which then led by creating an admin user to RCE, was the following. So here we have the duplicate roles in the JSON, and Erlang would see the _admin role, and the JavaScript validation, which checks if you're trying to create an admin, would see you're not trying to create an admin. So that's a very simple thing, actually, and once you know it, yeah, it's so simple that it's like that there's nothing to really mess with anymore, and you don't have to see that you have something stable like certain heap layout to massage and to put your payload in, but this payload just works every time. You have a vulnerable combination of those parsers. And yeah, fortunately for the attacker, almost all of the important logic in CouchDB is implemented in Erlang, which sees you're an admin, and the only validation which stops you from creating an arbitrary admin account would be the JavaScript implementation, which does not see that you're creating an admin. So that thing I used in a training I gave a while ago to showcase this type of bug, and it's very simple, it's concise, and it showed this concept really well. I think that's why I always like to show this bug. On the next example, a bit later in my Parser differential journey was a thing I found in my consulting time back at Security Labs. And it involved some Kubernetes, some Java, JSON Web Tokens, and the whole system looked basically like this. We had some user, some API user, a Kubernetes cluster with an ingress controller, and then the ingress controller would check the JSON Web Token if it's like correctly signed. It would just check the signature, expiry, etc., and pass it on to the router, and then it would go to the different backends. Different backends had another library which would decode the JWT, but not verify the signature. And as a good security consultant, you complain about this. You say, this is not good design. And then the customer says, yeah, but we verified the signature there, and you cannot have an unchecked signature over here, so this is probably fine. And then you have to come with a proof of concept or get the fuck out, right? This was, the top is the ingress code, the bottom is the backend code. It looks very, very similar. It's both Java and the ingress code does on the HTTP headers object get request headers get first for the authorization header where the JWT is inside, and then it returns that string if it like can parse it. And for the backend, it would get all the headers and then do a while loop over the headers, which first, at the first glance, seems like those two are equal. And back then, I didn't dig deeper into the HTTP headers implementation, but I did some dynamic testing and found that the get first would actually give you the last header if you have a duplicate authorization header, and the lower code for the backend would give you the first header because it goes over them in that in that direction. So we had the front end parsing bottom to top, and the back end parsing top to bottom, and they both would stop at the first authorization header they see. And that gives us this very simple, but I think very beautiful exploit that you just include 2 authorization headers. And the first one would be algorithm none, no signature, I'm the admin, whatever you choose as a payload. And the second one would be alleged signed JWT, which just is your actual user. And that was convincing enough for them to fix this, of course. I mean, there's no way to argue with this. And this brings us also to a question of like how to prevent this a bit. Or what would you do to not have this problem? Well, I mean, generally it's hard to avoid if there are 2 different parsers, but you can always have, it always helps that you don't pass on what you saw, but pass on to the next parser what you understood, right? So if you see one authorization header but don't see the other one for some reason, you then would just re-emit the HTTP header with the authorization header you saw, and thus omitting the fake one. Right. So I talked a bit earlier about stockpiling parser differentials. That idea is like great, and that was in 2023. I had no idea what this was good for. I found a parser differential in YAML between Python and Ruby. So I could make the same key under Python, output something different under Ruby. And I put it on Twitter, and someone asked me, hey, is this a bug you found? I was like, no, but I mean, it's a bug, but I have no use case for it yet. I haven't found anything useful. That was interesting. And then a year later, I had an idea. Now, I had to add Go to the mix and created a little magic YAML which would be parsed differently in Go, Python, and Ruby. And if you look at it closely, you will see that this example uses Python safe load, and this example uses the Python base loader, which are a bit different, and I cheated here a bit. But we'll see later on that the cheating wouldn't have been necessary. But that was at the time I added Go to the mix because I suddenly had a use case. But first, let's talk about how this parser differential works, like technically. This is how it looks. We have lang Python. We have exclamation, exclamation binary, some binary string Go. We have exclamation mark binary, some string Ruby, and let's go over this one by one. So the first example, we have a duplicate key in a YAML file, which is actually not a good idea and not allowed. Ruby will happily take the second key. Go will complain and yell at you that you have like already a key defined with the name lang, and it would just not parse this. Python will also take happily the second key. And now we saw this exclamation mark binary. This is called a tag in YAML, and it can be used to base64 encode arbitrary data inside YAML, which is a great idea. You can put it in values. You can store, I don't know, a movie or a GIF in YAML with like base64 encoding. But you can also use it on the keys. And this makes it interesting because some parsers understand it, some may not, right? So, second example, we got the binary base64 key, and this binary is just the string, the base64 string is just lang encoded as base64, obviously. Ruby will see the second, Go will 2, and the Python script will just see the first and takes the second binary string actually literally as string. So that's already a way to split out Python from Go and Ruby in that YAML file. So this double exclamation mark is a global tag. Those should be defined like in every YAML parser, and because I used the base parser in Python, it didn't know about it. Well, I don't know why, but it is like it is. And we also have a thing called local tags, which are defined per document. And those have a single exclamation mark in front of them. And if we try that with binary, then it gets interesting, because Ruby will just assume this is again base64 encoded and pick, in our case, lang 2. Go will pick lang 1 and take the binary string with one exclamation mark literal as a string. Python will do the same as Go. Cool. So the problem now we have is if we try to combine this, like with binary, with 2, and with one exclamation mark to split out Go and Ruby, Go will yell at us because we have a duplicate key suddenly, because it will take the literal string for binary and a double exclamation mark and single exclamation mark binary. It will treat them as the same key, so it seems like to not decode the keys before it compares if they are unique, but strips out the tags, which is funny. So the cool thing now is that we actually have a second parser differential in here, which is the base64 implementation, and we can use that. You see the binary string here, the BGFUZW. It has not the ending equal signs, and this is actually not correct, but Ruby, being Ruby, will parse it. And Go will yell at you and say, like, this binary value is invalid base64 data, which is great, because now we can use this to split between Go and Ruby that way, simply by doing this. So we take for Python, for the base parser, which is really stupid, we just take the key value pair, literally spelled out lang. For Go, we take the double exclamation mark binary with proper base64 for lang. And for Ruby, to avoid the collision, to avoid the duplicate key collision, we take the single binary, but make it shorter so Go doesn't see that we're actually trying to do the same thing here with Ruby. Make sense? How is this useful? What can we do with this? Why did I add Go to the mix? I mean, one thing which comes to mind with YAML, YAML is very present in stuff like Kubernetes, in infrastructure as code, and such things. And there are plenty of scanners for IAC code, which would tell you this is not secure, this is a backdoor, this is a malicious pattern, you should do this, you shouldn't do that. And you could bypass those scanners with YAML parser differentials, obviously. I tried it with 3 scanners. All 3 were easily bypassable, I think, with the binary tag. And I wasn't sure, like, is this really a vulnerability if we can bypass a boring scanner? Or is it not? I was a bit on the fence, so I contacted the vendors, all 3. Here's what I got. First vendor, head of security themselves. Thanks. I don't know. That might be a thing, but I'll ask my team. I'm not sure, though. And then he came back with, yeah, no, we don't do anti-obfuscation, but thanks, we might want to detect this weird binary tag. I didn't tell them about the single quote, a single exclamation mark binary tag. So I think their anti-obfuscation detection will be bypassable again very easily. Vendor 2, their psword replied, yeah, okay, I'll pass this to the right team. Never heard of them again. Vendor 3, no response at all. So if you want a green CI pipeline without any IIC scanner findings, use some YAML parser differentials. But that's not what we're here for. We want a shell, right? So last year, I found a bug which led me to add Go to the mix, and then Sergey made me submit it to the LangSec workshop, and I won, or the bug won the Parser Differential Award last year. So I was very proud of it. And here's the write-up from the workshop website. Subsequently, the verified dev file YAML is passed on to some Go binary in the dev file gem. Due to YAML being a complex format, the Ruby and Go parser differ a bit, and we construct a YAML file which doesn't have to seem a parent key in Ruby, but has one in Go. That's from the issue description itself. They put in the announcement, they put like 2 memory safe languages, both alike in dignity, are disagreeing here. It is a thing of beauty. It also drives home the point that no data format is so simple as to not need a mechanized definition, and formats considered to be infrastructure as code definitely should have one. So this is another way to approach this problem, having a proper definition which cannot be implemented wrong, but this is actually hard, and people will always write their own parsers. So I think this also won't really save us from this type of bug. But coming back to the actual bug I found, that is the CVE for it, and it was a parser differential partially. The parser differential actually enabled me to trigger a path traversal which led to an arbitrary file write out of a tar.gz file. So a classic bug hidden behind a parser differential. Because we have this workspaces feature in GitLab where you can have like remote VS Code on a Kubernetes pod running for you, and then you can do your development stuff remotely in that cluster. And these workspaces are defined by dev files that are YAML. And they had one feature which was explicitly disallowed in our implementation for parsing those dev files, which is called parent. Like it's just the parent key which would define basically a base dev file you inherit from. You can pull it from various things like Git repos or dev file registries, and this parent pulling mechanism had this file write primitive, but it was in Ruby it was not allowed to have the parent key, and then it was filtered out, and then the whole dev file was passed on to a to an external binary written in Go, which would do the actual parsing and have this vulnerability. So I had to first sneak around this, and then I could exploit the actual file write. So in this case, the parser differential itself isn't like, unlike in the other two examples, isn't really a vulnerability itself, but it enables a vulnerability. It's more a helper, like I would say some kind of same-side request forgery pattern where you also just can make a request to something, but you don't know where because it depends actually on the environment you're in. So I hope those examples were somehow a good showcase for the whole concept. I have some final thoughts and some pointers. So we had 3 different languages in one YAML file. And after I published this tweet where I had those 3 and the magic YAML and everything, someone approached me in a DM and was like, hey, wow, this is interesting. I think I found some more. And they sent me, in the end, they sent me this, which is like Ruby, Rust, Node, Go, Java, and Python. I will later on publish the slides. It's a link to a gist of them. And you can read it up. The whole write-up is somewhere on GitHub. And this was amazing because I really loved this. This is brilliant. It didn't work on my machine, but they provided the exact versions and had some Docker containers to run it. So your mileage might vary, but I'm pretty sure there is more than just those 3 languages. Also, in kind of relevance and actual good exploits, just want to list a few here for web and HTTP stuff. There's just too many. There's like tons of bypasses for web application firewalls or whatever you name it, HTTP, parsers, front end to some middleware to some backend, and they all like mess things up. And I think people like James Kettle or Orange Tie drop such stuff on a regular basis. Historically, I think that was 2013 or so. The Android master key, there was a APK signature bypass in Android because the zip files were parsed differently in C versus Java. Psychic Paper was iOS sandbox escape where XML comments were parsed differently within iOS in 2 different or maybe even more parsers. And Ruby SAML was relatively recent, like disclosed earlier this year. There were 2 XML parsers in a single library, Nokogiri and RexML. And those handled things differently, and then you could basically have a signed XML document where the signature points somewhere else, and you could freely choose the rest of the document, and the other parser would think like, oh, the document is signed, and it was like beautiful, really beautiful. To finish this up, just some general thoughts, like it's not easy to solve, and the more complex things get, the more complex data formats get, the more room is there for parsers to disagree on things, and the more room we have to combine those parsers and maybe shoot ourselves in the foot or find some nice application of parser differential. So by application, I mean vulnerability, right? And usually when you have a given differential, you have to put in some work to actually capitalize on it because it's always like very context dependent. So I would suggest we all like stockpile on those and go for it from here. That's it. Thank you.